Welcome back. This is DTFS of complex exponential by inspection example 2. We now make our complex exponential more complicated. In the previous example, we only had 3e plus j 0.2 pi n minus 0.5 pi, a single complex exponential. Now we add a constant minus 0.5 and we add a cosine. And can we still use inspection to find the DTFS of this? First is, of course, this signal is still periodic. A constant has no period. This is same period n equals to 10. What about this guy? So to solve this by an inspection, what we need to do is we convert all this into complex exponential. So minus 0.5 converting to complex exponential is this equation here. Why is this so? Y is minus 0.5 equals to 0.5 e j 0n plus pi. Okay, so if you write this out, 0.5 e j pi e j 0n. So isn't this 1? Yes. So this is 1 and omega equals to 0 radian per sample. That means every time we increase a sample, we increase by 0 radian. So e to the power j 0 n is always 1. What about e j pi? Well, e j pi is cosine pi plus j sine pi. And this guy is cosine pi is, of course, minus 1 plus j 0. So this is 0.5 times minus 1. So we get minus 0.5. Okay, so this is the idea. If you forget, then remember this equation, ej theta equals to 2 cosine theta plus j sine theta. So that's the equation we are using. Alright, so we have learned how to convert a constant into this complex exponential form. The second term remains the same. And now, of course, we are going to ask you to convert the cosine into sum of two complex exponential. If you don't know how to do that, please Google this, and this is the standard problem that we will always give you, converting a cosine or a sine into complex exponential. So out comes this. So basically, your original equation now is the sum of complex exponentials, which is almost exactly what DTFS is. So from this equation, we can perform by inspection to find CKs. Now the first trick is this, we need to find the period n. Okay, so we know that this term has a period 10 for omega equals to 0.2 pi. For 0.25 pi, the period is 8. So now the question is, since we have one with periodicity 10 and the other guy with periodicity 8, what is the common period for this xn? And the answer, of course, is that you can think of it that this guy would be periodic 10, 20, 30, 40, 50, 60, and so forth. Well, 8 will be 8, 16, 24, 32, 40, 48, and so on. And in fact, you realize that when n equals to 40 is the common period. So this is the least common multiple problem. And therefore, now we say that n equals to 40 is the one we need. So we can generate the fundamental frequency, which is 2 pi over capital N, the common period. And therefore, now we get 0.05 pi radian per sample is omega naught. So we now need to figure out what is k. So when k equals to 0, k times omega naught is 0 pi. So we need k equals to 0 to map to this 0 pi radian for this expression here. Then we need another k for 0.2 pi, and we need another k for 0.25 pi, as well as minus 0.25 pi. So let's work it out. So we have k equals to 4 will get us 0.2 pi. So we'll get we'll need k equals to 4 to express for 3ej 0.2 pi radian. And what about the cosine? We need 5 for this positive 0.25 pi, and we'll need minus 5 for this minus 0.25 pi. Okay, so we get k equals to 5 as well as k equals to minus 5. Now k equals to minus 5, later on you'll realize that we can get k equals to 35 will give us the same value as that. K equals to minus 5 for k equals to 35. Okay, so once we have done that, then we begin to plot our values, because all we are saying is that we already have found the expression over here.